In the last class, we saw that the loop gain of a negative feedback amplifier was very important parameter. That means this beta A, and it is this parameter which was appearing in expression for the overall gain, input and output impedance, bandwidth. So everything actually got affected by 1 plus beta A, and this beta A is the loop gain. So we will in this lecture try to see that given a negative feedback loop, how to find out this beta A. So we will try to find out and we will see that there are actually two ways in which this can be found out. So first we will list all the steps required for the first technique. Then we will apply that technique to two cases, two amplifiers, and then we will move on to the second technique. So in the first step, we set all the external input to the circuit to 0. That means we remove all the external sources. That means all voltage sources to 0 and all the current sources to infinity. That means we keep the port containing current sources open and voltage sources short circuited. Then in the second step, we break the loop at suitable point. So we will elaborate what do we mean by suitable point, how to identify the suitable point, and in case we are not able to find, then what step we need to take to break the loop. So there is going to be additional information related to step 2, but we will come to that later on. So once we have broken the loop, so we apply a test source, say Vx, at one of the two ends. So here also we will have to be careful that how to pick one out of those two ends. They cannot be arbitrary. And then loop gain. Once we have done this, loop gain beta A will be given by minus VO by Vx, where VO is the voltage at the second end, because at the first end we have already applied this test source. So these are the 4 steps, and we will have to be careful in step 2 and in step 3. So now let us take these steps and try to find out the loop gain of a negative feedback loop. So we know that we have this model for a negative feedback loop system. Here. So here we see that there are three locations where the loop can be broken. It can be broken here, or here, or here. So for example, when we try to break here at this location, then what we will have is A here, beta here, and the external input set to 0. Right? And then we apply, say for example, test source here, and then find out how much voltage we are seeing at the other end. So this is the first end, this is the second end of the broken loop. So once we find out this VO for choosing Vx, the beta A is going to be minus VO by Vx. Right? So this is how we will have to do. But as I pointed out, the location where we break the loop has to be chosen suitably, this point, otherwise there will be problem. So before we discuss how to identify the suitable point, we will talk about this third step. The test source should be connected at one of the two ends. So how to identify the which end the test source should be connected? So we see that in the original loop, signal will travel in this direction, in clockwise direction. So the end where we are going to connect the test source should be such that signal continues to travel in the same direction in the broken loop as well. So this is how we identify which node to connect the test source. So this is regarding the step 3. Now coming to step 2, that where to break the loop. So say in general we have this loop. So suppose this is the model of a feedback loop. Then if we decide to break the loop here, then what we have to ensure is that the impedance, and suppose this side becomes node 1 where we are going to connect the test source, and this will become node 2, and the signal here is, say for example, traveling in clockwise direction. Then we have to ensure that uh, the impedance that is looking into this direction is maintained after breaking the loop. For example, if this Z in is infinite, then when you break this loop and create this system, and you are going to connect your test source here, then even in this case, this Z in should be equal to infinity, right? Or in more general case, if this Z in is finite, then this should be also finite, or if it is not finite, then you have to terminate this with an impedance Z in, so that the second node after breaking the loop should feel that the impedance condition is same as was there before the breaking the loop. So to keep the thing simple, we try to break the loop at a location where Zin is infinite, but as I pointed out, it is not mandatory. If you're not able to identify a location where Zin at the point to be where you want to break the loop is infinite, then you just find out what is the input impedance looking into the node 1, and then you at the node 2 you put this input impedance, and then you can connect your Vx. So this is where you will get VO, and beta A here is also going to be VO by Vx. So we can take example of say this op-amp based amplifier. Right, so here we see that there is a loop here, feedback loop, and signal is traveling in this direction. So we have to break the loop, and suppose for a moment, typically we try to take this op-amp as ideal, but suppose we take non-ideal op-amp, that means this op-amp has finite input impedance Ri, and then we want to break the loop here. So in this case, if you break the loop, then what we will get is, of course, we set the external input to 0. So this is what we have done, and then after breaking the loop, we will have this scenario. Op-amp should be substituted by its model. And suppose it has some finite output impedance also. Here. So here we see that my op-amp is this much. This is op-amp. So we have taken non-ideal op-amps where we have finite input impedance and of course finite output impedance, and we decided to break here, right? So now here you can see that once you have broken this loop, the impedance here has become infinite, but the impedance looking in this side is Ri. So here if we connect our Vx and then try to find out VO here, we will get a wrong result for the loop gain because the impedance condition here and here they are not same. So this is node 1, this is node 2. So that is why what we will have to do is now at node 2 also we will have to put Ri and then find out VO. So this is what we will have to do when we assume op-amp to be non-ideal. But typically we will try to take the ideal, and in that case we will see that we can easily break the loop at this location here because the input impedance is going to be infinite, and after breaking also, what we will see at this location is infinite input impedance. Now we are going to take a more specific example and then try to find out the loop gain. So this is the circuit, and here this will be our usual output at this node, source of the MOS. Here we have op amp, and to keep things simple, we will assume ideal op amp. So we want to know what is loop gain for this circuit. So here we can see that there is a loop here. So now you can see that there are actually 3 points where this loop can be broken. Say here P1, here P2, or here P3. So we can break the loop at any of these 3 points, and let us first try to break at P1. So in the step 1, we will get rid of this input by short circuiting it. So step 1 and step 2. When we execute, we get this circuit. So here we have broken it. At P1. So here we connect our test source Vx, and then we try to find out this VO. Right. So here in this case, we can see that the input impedance looking in this direction is Z in equal to infinity. Right. So here input impedance is infinite. So when we break the loop, the second node, this is first node, this is second node. Second node perceives input impedance of infinite, which is same as what it was earlier in the unbroken loop. So we have broken the loop at a correct location, and we don't need to do anything additional here. So now we will just try to find out what is VO. Right. So we start from here and proceed towards VO to find out what will be the output voltage. So this is node 2 or VP2. So we first try to find out VP2. So this we know is going to be A into V plus minus V minus. So here V plus is grounded, V minus is Vx. So this is minus A Vx. Right. And this VO that we see here is the output of source follower amplifier. So this MOS is in source follower configuration, common drain configuration, right? And we will take lambda is equal to 0 to keep the thing simple. So we know that for source follower, the gain AV is given by GM-RL divided by 1 plus GM-RL, where RL is load. In this case, it is equal to R. So here what we have is the output is VO and the input is VP2. So VO by VP2 is equal to GMR divided by 1 plus GMR. That means VO is GMR VP2 divided by 1 plus GMR. So here we have already found out VP2. So this is equation 1 and this is equation 2. So we can multiply equation 1 and 2. So we get VO is equal to minus GM R divided by 1 plus GMR A into Vx. So minus VO by Vx is equal to GMR A divided by 1 plus GMR, and this is equal to the loop gain beta A. So we got this result by breaking the loop at point P1 here. Now let us, if we try to do the same thing at P2, then also things will be okay. We won't have to do anything else, because here looking into the gate of MOS, input impedance is infinite. So you can straightway break here at P2 also and calculate the loop gain. But now let us try to break the loop at P3 and then try to see that what happens. So here if we try to break the loop at P3, then what we get is this circuit. Of course, for step 1 and 2. So the load register now comes here. So here we see that looking from source towards the load, input impedance is not infinite. If you look into this direction, so we have a current going into this direction and in this direction. So here the current in this direction is 0. So this impedance is infinite. This is R. So this Z in is R. So at P3, the looking towards node 1, the impedance is R. But now if you break in this way, impedance is going to be infinite. So this is wrong way of breaking the loop. So what we will have to do, we have to put another resistor here, R, and then find out the output voltage, VO. So this is now the correct circuit for finding out the loop gain. Right. So we now take another example. So we now have inverting configuration. So this is the output of the amplifier, where op-amp is ideal and we have lambda is equal to 0. So in this case, we again have 3 points where the loop can be broken. This is point 1, this is point 2, and here point 3. So we see that at point 1, the input impedance looking in this direction is infinite. So here we can easily break the loop. Looking from point 3 also, we again have input impedance infinite. So here also we can break the loop easily. But here we have to be cautious. In fact, here we see that the input impedance is equal to R1 plus R2, because there will be no current into the gate of the MOS. So entire current will flow through these two resistors to ground. Right. So here it will appear that once we break the loop at P2, we'll have to terminate the second node with resistor R1 plus R2. So that is one way of doing that. Second is assuming that R1 plus R2 is very, very large, so that this input impedance also effectively becomes very large or infinite. And this assumption can be made here, because here we can see that the entire objective of this R1 and R2 is to create this feedback voltage VF, and we know that this VF is going to be decided by this ratio. So here the absolute value of R2 and R1 could be either large or small. This ratio can be maintained to any desirable value. So we take the liberty of this and then try to take R1 and R2 large, so that their sum is very large and the input impedance becomes very large, and the loop can be broken at point 2 also, right? So here we can now break the loop at point 2. Like this. And then connect the test source here at node 1, and we can keep the node 2 open. So this will be valid for R1 plus R2 very, very large. Right. So we can now try to find out what will be loop gain for this case. So VO, we know that is A into V plus minus V minus, and here it is going to be A into VP1. And this VP1 is the output of common source amplifier, which is being fed by VP3. So VP1 is minus GM RD into VP3. And VP3 from voltage division is R2 divided by R1 plus R2 into Vx. So we can multiply all the three equations. VO is equal to A into minus GM RD into R2 divided by R2 plus R1 Vx. So minus VO by Vx is A GM RD R2 divided by R2 plus R1. So this is the loop gain for the second circuit. Now we are going to talk about a second technique of finding out the loop gain. So in this technique, we have more freedom in deciding where to break the loop, but then we will have to do more calculations also. So here, first step is exactly same as that of the previous case. That means this is exactly same. In the second step, we really get the full freedom in deciding where to break the loop. So here we really have this freedom. We can break the loop at anywhere. We just won't have to worry about what is the input impedance looking towards the next node. But now this freedom is coming at the cost that we have to find out two quantities. So here we will have to find out what is called open circuit transfer function, HOC, and find a short circuit. Short circuit transfer function, HSC. So we have to do these two calculations. That means create two circuits for the broken loop, and once we have found out this, the loop gain is going to be given by this expression, minus 1 by HOC plus 1 by HSC. So here this is what we will have to do, and for finding out HOC and HSC we have to set up a different circuit. So suppose, for example, after breaking the loop, this is the scenario. That means finding HOC and HSC. So for HOC, this is the circuit we will have to set up. So we have, of course, broken the loop, and then we connect a test source Vx, and as the name suggests, we try to find out the open circuit voltage here. So here HOC is going to be VOC divided by Vx. Now for finding out short circuit transfer function, we, as the name suggests, take the help of short circuiting. We will have to do the short circuiting, but this time we use a current source to excite the circuit. So we excite with current source and then find out the short circuit current at the other end, and in this case HSC is going to be ISC divided by IX. So we'll have to carry out these two analyses, but of course usually they are not going to be very difficult, and then beta A is minus 1 by HOC plus HSC. Now let us return back to example 1. So here we have ideal op-amp, MOS, and register R in source follower configuration, and for this case we have to find out loop gain. So here we are truly free to break the loop wherever we want, and we will try to break the loop at this point 3, where we saw that the previous technique requires us to terminate it with R, additional register, because this impedance is not infinite. So now let us trace the step using this second technique and try to find out the loop gain. So first we have to find out open circuit transfer function. So for this case, we break the loop like this, and this is going to be open circuit voltage that we are looking for, and here we will excite it with test source, and we set the external input to 0. So this is what we have to find out for this circuit. Right. So for this case, we will have to draw the model of this MOS to find out this VOC. Right. This will be in terms of this voltage VP2. So we are taking lambda is equal to 0. So model is going to be this one. So gate is getting excited by VP2. Drain is grounded. Source is open. And in this circuit, we have to find out what is VOC. Right. So here we have current IG. We know that IG is equal to GM VGS, and VGS is going to be VP2. Source is VOC. So this is the current, drain current, and here since this path is open, so this current IG cannot flow and it has to be 0. So IG is equal to 0. So this says that VOC has to be equal to VP2. So we now know this voltage VP2 here, and from op-amp we know that VP2 is also equal to A into V plus minus V minus. So V plus is grounded and V minus, this V minus is actually connected to Vx. So this is 0 minus Vx. So from this equation, say 6 and 7, this implies VOC is equal to minus A Vx. So that means VOC by Vx, which is transfer function, open transfer function, is minus E. Right. So now we have to find out short circuit transfer function. So for this case, we have to create a different circuit, but we again break the loop at this location, that is node 3. So we set the external input to 0. We have here resistor R, but this time we are going to excite this node 1 by a current source Ix, and this time the other node is going to be short circuited, and what we have to find out is this short circuit current. So if you know this, we know the short circuit transfer function. So this is Vp2, right? So for finding short circuit also, we draw the model of MOS. So we have this IG, GM VGS, drain is short circuited. This time even the source is also short circuited, and the MOS is getting excited by Vp2. So here we see that ISC is equal to IG, which is equal to GM VGS. So ISC is equal to GM, gate is Vp2, source is grounded. Now we have to find out this Vp2. So we see that we have this V minus, which is voltage developed across R because of current Ix. So here we have Vp2 equal to A into V plus minus V minus is minus A V minus, and this V minus is R into ISC. So here we have the equation 9, and this is equation 10. So we multiply equation 9 with equation 10. So we get ISC as equal to GM into minus A R, no, sorry, this one is test source. So here we find ISC divided by Ix is minus A GM R. So the short circuit transfer function is minus A GM R. So we have found out short circuit transfer function, and open circuit transfer function we had already found out, which was minus A. So therefore the loop gain is equal to minus 1 by HOC plus 1 by HSC. So here we see that this is going to be So you recall that we got exactly same result here, and that result was basically the voltage gain for source follower multiplied by the gain of the op amp. So this is what we had got earlier. So here we see that we have freedom in deciding where to break the loop, but then we have slightly more calculations, although easier to carry out. So we can use any of these two techniques to find out the loop gain. The references for this lecture for the first technique. One is Rajavi, and for technique 2, Sidra and Smith.